Hi everyone, welcome back. In this lecture we're going to continue looking at rooted trees, but we're also going to get into spanning trees of graphs. Now it's quite common to represent data as a rooted tree. For example, web pages under the hood are essentially a rooted tree. It's known as the DOM, D-O-M, or Document Object Model. And the idea behind that is in order to add interactivity or responsiveness to your web page, you need to be able to interact with the DOM. So as a user does something, you may have to go into the tree and make some changes to your DOM, to your document object model. So being able to design responsive web pages requires an understanding of the rooted tree that's sitting in the background. Other places that rooted trees are used, for example, is right here in our first example. This is a rooted tree which encodes an expression, a mathematical expression. What is the formula that this encodes? And so we're going to investigate this throughout this lecture. So our goal today is to take a little bit more thorough look at rooted trees. Specifically, we're going to be interested in how to walk through a rooted tree, visiting each of the vertices. And there's going to be a number of ways to do that, and those are what we're going to discuss today. Before we get to that, we're going to talk about what an ordered rooted tree is. So for some applications, it is essential not just to have a rooted tree, but also to have an ordering of the children for each internal vertex. So as a basic example, let's think of the table of contents in a book. So here they're listed out with an indentation, which really tells you that, okay, we've got a book. There's 3 chapters. The first chapter has 2 sections. The second chapter has 3 sections, but in the second section there's a subsection. And then the last chapter has no sections. We can visualize this as a rooted tree as follows. So there's our root. It's a book. Now at the topmost level, the book consists of 3 chapters. There's chapter 1. There's a chapter 2. And there's a chapter 3. Now the thing to observe here is that the order matters. Chapter 1 precedes chapter 2, which precedes chapter 3. So this is what we mean by it might be desirable to have an ordering of the children. There's 3 children here, but we also want them ordered in a specific way. Chapter 1 is the first child, chapter 2 is the second child, chapter 3 is the third child. And then from that, chapter 1 has a couple of sections, and they also have an ordering to them as well. So there's a first section of chapter 1, and then there's a second section of chapter 1. Chapter 2 has a first section, a second section, and a third section. And it just so happens that the second section has a subsection. So section 2.2.1. And then chapter 3 has no sections. So there's a rooted tree, actually an ordered rooted tree diagram of the table of contents of a book. We also have listed them by their levels, the root or level 0, the chapters being level 1, the sections being level 2, and the subsection being level 3. So we can even jot that in here. This is level 0. We've got level 1, level 2, and level 3. Now in some applications, we'll be interested in walking through a rooted tree and visiting the various nodes. So how can we do that? How do we walk through and process a rooted tree? Well, 2 common ways of doing that are known as the preorder traversal and the postorder traversal. So we'll do examples of each of these. What they are is the preorder traversal. These are both defined recursively, but the preorder traversal of a tree, it first visits the root vertex, and then after doing that, it visits in preorder, so that's the recursive part of it, the vertices of the subtrees. And the subtrees, we've listed them as T1, T2, and so on. So we're thinking of this as an ordered rooted tree. where T1 is the first subtree, T2 is the second subtree, and so on. So let's have a look at an example. So we'll consider a rooted tree with root A, and it has a first child B and a second child C. C itself has two children, a D and an E child, and then D will have two children, an F and a G child. So this is our rooted tree, and we're interested in finding a preorder traversal, and then we'll do the postorder as well. So what is a preorder traversal? Again, it's just a way of visiting all the vertices in the tree, and we do it in this way. It says, first visit the root vertex. Okay, so I'm at the root vertex, and then we just write down the vertices as we visit them. So I'm at the root vertex. There we go, and I'll just check it off as I go along. Now we visit the vertices in the subtrees T1, T2, and so on in a preorder fashion, in a preorder traversal. So then I say, okay, there's two subtrees. There's that one, and there's that one. And so I visit them in turn. I first go through the subtree T1, and I visit it in preorder fashion. It's only got the rooted vertex, so that's B. So I visited that one now. And I'm done with that T1 subtree. Now I go and visit all the vertices in this subtree. So to do that, I go ahead and I visit the root of it. And then I visit the vertices in each of its subtrees in preorder fashion. And so then I go to work on this subtree rooted at D. Visiting it in preorder means I visit the root, and then I visit the vertices in the subtrees of that root. And those are both just single nodes. So then we have that we visit F, and then we visit G. So now I visited F, I visited G, therefore I visited all the subtrees of D. And so I've done processing this part of the tree. And so now I can go ahead and process the next part. So I'll add our check marks. We've done D, then we did F and G. So then we go back up and we say, is there any subtrees we haven't done yet? Yep, we haven't done this subtree of C. So we can go ahead and visit its nodes in preorder, and that's just the root. And so that's E. And so now I've done E, and we can see the check marks from everything that we've actually done all the vertices. So we've done our preorder traversal, and this is the listing of the vertices as we have visited them in preorder. Another way we can visit the vertices of a rooted tree is in postorder. And what is postorder? Postorder says, visit in postorder the vertices of the subtrees first, and then visit the root. So if we think about our, this is a root, it's the parent, these are its children. Then what preorder is saying is visit the parent first and then the children after. So preorder is a parents first approach. So this is a parent first. Kind of think of this as like the air mask coming down, or the oxygen mask coming down from above the seats in an airplane. You're instructed to always, parents put on theirs first before the children. So preorder traversal is like the oxygen masks on an airplane. Parents are first. What about postorder traversal? Postorder says you visit the subtrees first and then the root after. So that means it's a children first approach. So in this case, this is a children first. Kind of like how you would rescue people off a sinking ship. Children first, and then parents after. So postorder, children first, preorder, parents first. So let's go through our postorder, visiting all our vertices. it says, okay, visit in post order all the subtrees first. And again, the subtrees are listed in order. So this is an ordered rooted tree. This is the first child of our root. This is our second child. So this says to visit in post order the subtree rooted at the first child. And so that means I will visit all of its children, but there are none. So then I visit the root of that subtree, which is B. So we've dealt with that one. And now what do we do next? Well, we still haven't finished all of the children of the root. There's still this child here. And to do a post-order traversal of the subtree with this child means we're doing a post-order traversal of that subtree. And in order to do that, we deal with its children first. So it's got 2 children. And I will do a post-order traversal of the subtree of the first child. But in order to do that, I have to process the subtrees of its children first. It has 2 children, and so I will process the subtree of the first child. And that child has no children, so it's the subtrees T1 and so on. There are none of them, and therefore I visit the root of that subtree first. And so that's the F. So I've done that one. And then I do the next child of D, and that's the child G. It has no subtrees off of it, it's just the root. So now I visited G. And then we come back and now we can process the parent. That's D. And now I've dealt with the first child of C. Now I can deal with the second child of C. And that's just E, because it doesn't have any children, so I process the root of that subtree. Now I've dealt with all the children of C, so now I can process the root, which is C. Now I've dealt with all the children of A, and so now I can process A. And there's a post-order traversal of this rooted tree. So that's a way to visit all the vertices in the tree, and this is known as a post-order traversal, or visiting them in post-order. I should include a little check mark because we've now visited A. So one nice way to think about the pre-order versus the post-order. Post-order is a little bit more challenging to get because you got to go all the way down the tree, process, and then sort of backtrack. Whereas the pre-order, I like to think about processing in pre-order in this way. Visit A, and then just sort of outline the tree. Then I visit B, then I visit C, then D, then F, then G, then E. And if I do a little trace like that, just tracing around the outside of the tree, then what I get is a pre-order traversal as I encounter the vertices. If I've already encountered it before, so for example, if I've encountered C here, then I don't worry about it when I come near C again. I just only process the ones I haven't already processed. And that gives me a nice way to come up with the pre-order. The post-order is, it's not so quick as to just do a little trace like that, but we can certainly do the post-order as we've done in this example. Go all the way down first. I'm interested in A, process its children first. B, then process child C. But to process child C, I go all the way down and process its descendants first, and then G, and then process D, and then back up to E, and then C, and then back up to A. All right, so those are the 2 kinds of traversals we have for visiting all of the vertices in a ordered rooted tree. I want to point out, though, that these are not unique. So post-order traversal, if I have a tree that has this as its post-order traversal, it may not be that tree. They don't uniquely define the tree. So this is just something to note. Traversals don't uniquely define the tree. For example, if I look at this rooted tree, A, B, F, G, D, E, and C. So if this was our rooted tree, then the post-order traversal of that would be B, F, G, D, E, C, A. And that's precisely the same as the post-order traversal of the tree we started with. So we can have two different rooted trees that give rise to the same traversals. So they don't uniquely define it. That's just something to keep in mind. But it is a way to go through and process all of the vertices on a rooted tree. So let's look at another example. So in this case, we want to draw an expression tree for this arithmetic expression. And then we want to give the post-order traversal. So what does it mean to draw an expression tree? Well, what we're going to do is we're going to draw a tree where the operations get done on the children nodes. So for example, if I look through this expression, I see that what I'm doing is I'm adding together two things. So the very last operation I'm going to do is an addition. So we have addition being done on two smaller expressions. The first smaller expression is 3 times 5. So that expression, there's a multiplication, and it's being done on 3 and 5. The other half of the addition expression involves this one here. And this is a multiplication of two objects. So it's a multiplication of some expression, 7 minus 4, and 2. So in order to do that one, I'd have to work out the subtraction, and that would be 7 and 4. So there's an expression tree for that arithmetic expression. This tells me that in order to work it out, I would first have to do a 7 minus 4, get that value, then I can do the multiplication of that value and 2, and then I'll just hold on to that value because I need to add it to the result of this one. And then once I've worked out this value and this value, then I can go ahead and do the sum of them and get the result. So this is the rooted tree that is a diagram for this arithmetic expression. Now what we want to do is a post-order traversal of this. So let's look at the post-order. So post-order traversal says start at the root, do the post-order traversals of its subtrees. So that means I'm going to first do the post-order of this one. Post-order of that one says, okay, starting with that root, post-order traversal each of its children's rooted trees, and then visit the root. So this means we are doing a 3, a 5, and then we are coming back to the multiplication. And so now I've dealt with this child subtree, and now I can go ahead and post-order traversal this one. So to post-order traversal from that root, I come down and I post-order this subtree first. Post-order of that is 7, 4, and then visit the root, which is minus. And then post-order traversal the second subtree, that's just 2, and then do the root, and now I've dealt with that. So I've done both of these now, and now I can come back and visit the original root, which is the plus. And so there's a post-order traversal of that rooted tree. We can go ahead and also do the preorder. It wasn't asked here, but let's go do the preorder. And again, remember, the quick way to do the preorder is to just start at the root and then just wander around writing down the nodes as you visit them. And so that means preorder is plus, multiply 3, 5, multiply minus 7, 4, 2. And there's our post-order traversal. Now you may be saying, why do this? Why make a post-order traversal or pre-order traversal for this expression? I very well know how to evaluate this. Why would we even do this kind of thing? Well, one of the nice things to notice about this is I don't require any parentheses to make sense of how to do the calculation. Notice I had parentheses up here. I don't have any in these expressions. Have I lost anything by not including parentheses? And the answer is no, because if I look at this, I see a multiplication. That multiplication follows two numbers. So that means this multiplication is really telling me that I'm going to be multiplying the two values preceding it, the 3 and the 5. What about the subtraction? I'm going to be subtracting the two values preceding it. And if we look at our tree, we see that those are just the two places we could start at for doing the evaluation. What about the multiplication here? Well, if I look at that multiplication, it says I'm going to multiply 2, 2, oh, what's preceding it is a subtraction, which means I can't do the multiplication until I've finished the subtraction. And I can see that here. I can't do that multiplication until I've processed this subtree first. Or, back in our original expression, I can't do the multiplication until I've done this first. What about the addition? The addition requires me to do a multiplication, and then there's also the 2 here. So there's a multiplication that has to be done. It's going to involve some expressions beforehand, and so I have to process the things before it before I can do those latter operations. This is as opposed to what we call an in-order traversal. So I didn't define this above. In-order only makes sense for binary trees, so trees for which every internal node has at most 2 children. What would in-order be? Well, in-order would be the following way we would visit these nodes. We'd start at the root, visit the left tree first, then visit the root, then visit the right tree. So that's what in order would be. And so we'd visit the left tree first. To do that, we would visit the 3, and then we'd visit the root, and then the 5. So in order would be visit 3, then the root, then the 5, then we'd visit the root, which is up here now, and then we'd visit the subtree on the right. The way we'd visit the subtree on the right is in order. So we'd visit the left subtree, the root, then the right subtree. So this means I would visit 7, then the subtraction, then the 4, then the multiplication, then the 2. And so what we see is that in order is precisely our original expression, just without the parentheses. Do we need the parentheses? Well, in this case, when I look at this in order, if I want to actually get back to the original meaning of the expression, well, I can't just use order of operations to get that, because order of operations would tell me, well, do your multiplications before you do your addition subtractions. So I would do these two first, the 3 times 5 and the 4 times 2 first. But that's not what this original expression is telling me. It's telling me I need to do the subtraction here before the multiplication. So in order is ambiguous in the sense that we still need those grouping brackets to tell us how to evaluate it. So we lose meaning from the in order. However, post and pre-order, we don't lose meaning. We actually get instructions for evaluating the expression without the need for parentheses. So let's actually see this a little bit more thoroughly in this next example. So preorder is also called Polish notation, abbreviated as PN for short. And the postorder is also called reverse Polish notation, or RPN for short. HP calculators use postorder and a stack to evaluate expressions. And we'll do an example of this in a second, but what I want to do is just do the very first part of the postorder traversal. So here I'm drawing my stack, and in the postorder traversal up above we have a 3, a 5, and a multiplication. So what that means is as I read through that expression, I'm going to put 3 into my stack, then I'm going to put 5 into my stack, and then I'm going to put multiplication into my stack. So I'm imagining that in my stack I'm loading things at the bottom end. So I put 3 in, and then I'm going to put a 5 underneath it. So I slide the 3 up, then I put a 5 in my stack, and then I'm going to put the multiplication in my stack. And so my stack looks like this right now. And what a stack does is it processes last in is the first out. So it's processing the stuff that I've put in last. It'll process those first. And so the last thing I put in was the multiplication. So that means what it's going to do is it's going to multiply the previous two things I put in the stack, and that's the 5 and the 3. So this will evaluate to 15. And so this is how HP calculators work. They use reverse Polish notation. And so just so you can see this in action, I've brought out my HP calculator from 20 years ago, actually 20 plus years ago. This is the one I used to use in university. And the way we're going to do our evaluation is just as we define there. Suppose I want to multiply 3 times 5. The first time someone picks up an HP calculator like this is they want to do a multiplication, so they go 3, and then they hit the times button. And you can see error, 2 fewer arguments. And they're often confused. What does that mean? I haven't put in the other value yet. And the idea is, yeah, and that's the problem. Multiplication takes 2 inputs. As soon as you hit the multiplication sign, the calculator is going, well, where's my 2 inputs? You never gave me 2 inputs. I can't multiply just one thing. So that's where this stack comes into play. So I have to load into the stack the number 3, and then I load into the stack the number 5, and you can see them now stacked up there, and then I multiply them. So I hit the multiplication sign, and that gives me 15. And so that's how you work with basic arithmetic on these calculators that use reverse Polish notation. So let's actually go ahead and look at our expression that we have drawn the tree for and did the post order traversal of. It actually is the instructions to evaluate it. So it says, as we read from left to right, 3, put it in the stack, 5, put it in the stack, hit the multiplication sign, put 7 in the stack, put 4 in the stack, hit the subtraction sign, put 2 in the stack, hit the multiplication sign, and then hit the addition sign. And there we go. We've got our answer to that expression. So the post-order traversal was the instructions for evaluating that expression. And the key observation is that we did not need parentheses to make sense of that. So this was exactly the instructions we needed. So let's jot it down here. The way it works is we've got our post-order traversal. And the way it worked was we entered the 3 in, we entered the 5 in, then we hit the multiplication sign. So that evaluated that to be 15. And then we entered the 7 in, and then we entered the 4 in, and then we hit the subtraction sign. So that evaluated out to 3. And then we put the 2 in, and then we did the multiplication. So it took the multiplication and applied it to the previous 2 entries in the stack, which was the 3 and the 2. So that evaluated out to 6. And then it took the addition sign and said, okay, now add the previous 2 things in the stack. The previous 2 things in the stack was the 15 and the 6. And so add them up, and we get 21. And so that works out to have a value of 21. No parentheses required. And this is the key observation. Reverse Polish arithmetic doesn't require parentheses. And so this is a great way to encode arithmetic expressions in a computer because you don't need this redundancy of parentheses. So this is definitely worth noting in terms of post-order, pre-order, in-order. How do they compare for arithmetic expressions? So if we put operators are like addition, subtraction, multiplication, division. If we put those before the operands are the actual numbers. So if operators are before operands, then this is preorder, or often referred to as prefix notation. And again, it's often referred to as just Polish notation. And so that's this here. Preorder is often called Polish notation. So, and that's when the operators are before the operands. So if I look up here at preorder, I see the multiplication sign. That means it's preceding the two things I'm going to be multiplying. So the operator is before the operands, as opposed to operators. So leave a little bit of room because I'm going to put a line in between these two. Operators after operands. That is our post order or postfix notation. And that's also referred to as reverse Polish notation. And that we've seen up here, that when the operator is after the operands. Now, what about the case where the operator is between the operands, which is our usual notation, the one we use anywhere we've been writing mathematics out, doing algebra or arithmetic? We always seem to use the in-order notation. So this is by putting the operators between the operands. And that's known as in-order or infix notation. And that's our standard one we use when writing things out. Now, when it comes to computing and giving instructions to a computer to do these arithmetic operations and evaluation of expressions, the key observation here is that if I use operators before operands or operators after operands, in other words, I'm using preorder or postorder notation, then this doesn't require parentheses. So this will be a parenthesis-free notation. There's no ambiguity in the expression when you've used preorder or postorder notation. There's only one way to evaluate the expression, as opposed to using infix notation. This needs parentheses. And if you want to avoid, in some cases, the need to put parentheses, then you need an order of operations and order of operations. So things like, if it's unclear because parentheses aren't telling you to do one thing over the other, then do the multiplication and division before you do the addition and subtraction. So that's what we mean by order of operations. The order of operations that you probably learned in elementary school for which expressions to evaluate first in a longer expression. That's only required in our infix notation. In preorder or postorder notation, we don't need parentheses and we don't need an order of operations. We just proceed from left to right and do the expressions as we encounter them. So that's it for the first part of this lecture on ordered rooted trees. Here we just looked at different ways that we can work through or search through or process the vertices of an ordered rooted tree. We had our preorder traversal, our postorder traversal, and then I also brought in the in-order traversal just because that gives rise, in this case of arithmetic expression, it gives rise to expressions that we've basically been using ever since we've started doing arithmetic. So I just wanted you to see how it relates here. But postorder and preorder for representing expressions in a computer, this postorder and preorder traversals are the way to go. And so in the next part of this lecture, we're going to get into spanning trees and then how to search through the vertices of a graph using a spanning tree. And this will give rise to the depth first search and the breadth first search algorithms for searching through the vertices of a tree. Two extremely important searching methods for graphs. Two of the fundamental graph theoretic algorithms that one needs if one's doing anything in computing science with graphs. So we'll get to those in the next lecture.